having looked at ray tracing as an idea and at convex lenses, let's try ray tracing with convex lenses. So we'll try a convex lens, and we will stick the object outside the focal length. A convex lens, as you know, looks something like that. I'm going to replace it with an ellipse because it's pretty close and it's a whole lot easier and faster. So we'll start with an ellipse. Like this. We don't need text in it, and I will place this in some location and we'll just kind of get set up. Here is a line running right down the middle of my lens, and here is a primary, principal, optical axis, whichever word you like. Now we'll get some numbers in here. I'm going to put the focal length at 20 centimeters, and I'm going to pretend these dots are all a centimeter apart. So my focal point is over here, because for a convex lens, remember my rays are coming in this way, and they all converge onto a single point. So my focal point is going to be over on the right side. This is F. I'm going to reflect my focal point across to the left, and that's going to be my F prime. So my F, my focal length, is going to be, in this case, 20 centimeters. And now I would like to put my object outside of my focal length, so I'm going to put my object at 45 centimeters. For my object for ray tracing, I like to use just an arrow, and I use an arrow because an arrow is really straightforward to draw. One end of it is a point, the other end of it's flat. If I can put the flat end on my optical axis, I don't even have to do anything with that, and I can just worry about moving the point. So I would like to draw my arrow right here. What I was saying about an arrow being convenient, any point that's on my optical axis is going to stay on my optical axis. So when I can trace out where this point ends up, if it ends up here, I can say here's that, and that stays on my optical axis, and all I have to do is trace out one location, which makes my life really easy. So what I've got is a focal length of 20 centimeters. I've got my object out here. I said my D object, that's my object distance from the lens, is going to be 45 centimeters. And my H object, which is the height of this thing, I made this thing 10 centimeters tall. Now I'm ready to get started. So now I'm going to do this ray tracing thing. I'm going to say ray 1 is going to travel parallel to my axis and then through F. What I mean by that is I'm going to travel parallel to my axis until I hit the middle of my lens, and from there I'm going to go through my focal point. There is ray 1. Ray 2 is going to go through F prime and then parallel. So I'm going to start here. I'm going to go through F prime just until I hit my lens, and then I'm going to exit parallel. There's my ray 2. And what I see is that they intersect right here. So I'm going to draw the tip of my arrow right at that location, which is here. Here. This is my image. My image is upside down, so let me get rid of this background in just a moment. My image is upside down, which I say is inverted. It is a real image, meaning it is made out of actual light rays. This will make more sense once we look at a virtual image, which is the opposite. But for right now, it's a real image, and it is smaller. So I have an image distance of 36 centimeters, if I count, and I have an image height of 8 centimeters, but it's upside down, so I'm going to pick up a minus sign. That minus sign corresponds to this thing being inverted. Now I am going to get rid of this background, and I want to try and see what I can do with this. I have a separate quantity called magnification. And magnification is what it sounds like. I'm going to define it as the image height divided by the object height. In this case, that is 8 centimeters over 10 centimeters. The 8 is negative, and I get a negative 0.8. I can pull a couple of things out of this. This is negative, which tells me I am inverted. And it has a magnitude. Magnitude of my magnification is less than 1, so I am reduced, or diminished, sometimes you'll see. A different definition for magnification comes from the distances, and it looks like this negative di over do. I want to test that one out, so I'm going to get a negative. Di is 36 centimeters. Do is 45 centimeters. 36, that's 9 times 4. 45, that's 9 times 5. The 9's cancel, so I'm left with 4/5, which is 0.8, and I've got that minus sign, negative 0.8. This checks out. This magnification equation is one that we'll use quite a bit. Height image over height object, or negative d image over d object. Sometimes you use, the left side of this thing. Sometimes you use just that part, and sometimes just the right side. It depends on what your situation is. Magnification is a centimeters over centimeters, meters over meters, whatever, so it is a unitless quantity. And that is it for a convex lens ray tracing with the object placed outside the focal length.